Dear audience, my name is Robin Chan. I'm a doctoral student at the University of Wuppertal, and I'm happy to present here at this year's ICCV. I'm going to present a work which is a joint collaboration together with Matthias Hottmann and Hanno Gottschalk, both also from the University of Wuppertal. And the title of our work is Entropy Maximization and Meta-Classification for Out-of-Distribution Detection in Semantic Segmentation.
Speaking of semantic segmentation, this task can be described as clustering pixels in an image that belong to the same object class. Here we assign each pixel to one color, and one color corresponds to one class. In recent years, neural networks have been established as the main tool for semantic segmentation, and those models are usually trained to operate on a closed set and predefined set of object classes. And when objects cannot be assigned to one of the predefined set of classes, in other words, those objects are outside of a model's learnable semantic space, they are considered as out-of-distribution objects according to the none of the known principle. As an example, let us consider animals. Animals are out-of-distribution objects for models trained on the cityscapes dataset because they don't appear in the training data at all. However, when we present animals to a model which was trained on cityscapes, it has to assign it to one class. It doesn't have the option to say, I don't know, and the assigned class is not animal. Therefore, the prediction on OoD objects is unreliable. And this is where entropy-based out-of-distribution detection comes into play. The goal is to identify regions in an image where out-of-distribution objects could appear. What we saw was that neural networks produce unreliable predictions for out-of-distribution objects. One desirable property would be that they at least output a high prediction uncertainty on those objects. And prediction uncertainty can be quantified by various measures, such as the softmax entropy, which is defined as this formula. In this work, we approach out-of-distribution detection by enforcing neural networks to output a high softmax entropy on out-of-distribution samples. In our experiments, we use two data sets for training. One data set is cityscapes, which we use to draw in-distribution samples from. As a second data set, we use COCO, which is a large collection of everyday objects in everyday scenes. We remove all images with instances that could also appear in cityscapes, and we use the remaining subset as out-of-distribution proxy. Then we perform out-of-distribution training, which aims at minimizing the following multi-criteria objective. It consists of two separate loss functions for in-distribution and out-distribution. For in-distribution samples, we use the negative log likelihood of the target class. This loss function is also commonly known as the cross-entropy loss. For out-distribution samples, we use the negative log likelihood, which is now averaged over all classes. What we realize is that minimizing this particular loss function is equivalent to maximizing the softmax entropy on out-of-distribution samples. We observe that after OoD training, we have a better separability between in-distribution and out-distribution by means of the softmax entropy. By thresholding on the pixel-wise softmax entropy score maps, we obtain pixel-wise out-of-distribution prediction masks. The pixel level evaluation shows that we can significantly improve our OoD detection performance on two separate datasets, which is the lost and found dataset and the Fishyscapes dataset. This is achieved by sacrificing only a marginal loss of original segmentation performance, which was the semantic segmentation of cityscapes of only 1 percentage point. Due to OoD training, we increased the sensitivity towards predicting out-of-distribution objects. This could also lead to false positive indications, which is why we apply meta-classification as a post-processing step. We construct handcrafted metrics, which all can be derived from the softmax probabilities, and feed those metrics through a logistic regression to remove false positive out-of-distribution predictions. Due to OoD training, we are able to identify out-of-distribution objects which have been previously overlooked. This will also produce some false positives here on the road, which we are able to remove by applying meta-classification. And this is how we approach out-of-distribution detection in semantic segmentation. Thank you for listening.